Today I'm going to talk to you about the GM over ID technique for designing common source amplifiers. Now, this technique might seem new or completely different from what you're used to, which is normally designing in strong inversion, which means your gate to source voltage is greater than the threshold voltage by 0.3, which is a rule of thumb. However, in modern design, one can't always guarantee that level of VGS as you're shrinking power supplies. Also, the assumption that MOSFETs conduct no current between the source and drain when VGS is below VT is simply not true. And in fact, there's an exponential region where the MOSFET equations actually look a little bit like BJT equations, and below threshold design is actually a place where you can get the maximum gain for a common source amplifier. One thing to remember is that all the analysis, small signal analysis techniques that you've used so far for common source, common gate, common drain, whether you've used a source transistor or not, or whether a source transistor is bypassed by a capacitor or not, this is all the same. What the GM over ID technique does is just allows you to choose your drain current and your gate to source voltage so that you can more straightforwardly design your common source amplifiers. So let's get started. So what we have here is a VGS VDS versus drain current plot, and over here you can see the MOSFET. It's called a diode connected because the drain and the gate are both connected to the same point, and we're sweeping that voltage. And we are measuring this current. And in a normal plot, it looks like, yeah, 0 amps right up until about the threshold voltage. Starts to curve up a little bit and then starts to rise even more. Well, the thing is we can really see what's going on with this device if we take, in this region, we just take the log. And you can see that when we take the log of an exponential right in that region, we get a looks like a linear relationship, which in this case means an exponential one. And over here, if we take the square root of ID, we're kind of getting a straight line above threshold voltage. Well, if you take the square root of something that is squared, you should get a straight line there. Now, moderate inversion, which means you're not sub-threshold, you're not above threshold, but you're near threshold, those equations are a little bit difficult, and in general you need a numerical simulation to solve for that. So we're actually not going to go over those equations. Now you can download this file, run it, and all you have to do to see the logarithmic part is just take the log, and then you can go and take the square root to get the strong inversion part. So let's talk about weak inversion. Now, weak inversion just means that you're well below the threshold voltage of the device. GM is still the derivative of the drain current with respect to the gate to source voltage. But in this case, rather than the GM that you're used to in the textbook, we actually are taking the derivative of this equation here, and when we simplify it, it's simply ID over an ideality factor and a thermal voltage. Now this is a thermal voltage, 26 millivolts at 300 Kelvin. And it is not the threshold voltage. It's just how warm everything is. These values here come from a SPICE deck. and they are only accurate for the 27000 or the 27002. So if you have this data, you can extract it just like you would do for the diode. Is you take the log, you find 2 points, and you can find IS and you know what VT is. The applications are low power and low noise and low frequency. Because you're not applying a large gate voltage, you're not banging the electrons into the surface of the MOSFET oxide layer, and so there's actually less noise, and you can achieve noise levels of equal to a BJT for weak inversion. Now moderate inversion, if we can see that there's this, I guess have to call it a curvy spot. Right here it's straight because I've taken the square root of ID. So if I'm taking the square root of something that depends on the square, I should get pretty close to a straight line. Well, this isn't a straight line. It's moderate inversion, and it's a trade-off position between power, noise, and frequency. Now, just because it's a little bit harder to come up with a hand calculation doesn't mean that it's not a valid place to design. Now, we can plot all of these together, and you can download this plot and run it. And so I've got 3 approximations: the weak inversion in green, strong inversion. It's a little bit hard to see, but the squared you should see that. All right, and then the full EKV spice model, which you can see all these parameters up here. So I'm just trying to plot ID. Well, you can see that the red, the full model from Spice, can be seen as to be can be seen from weak, moderate, and strong inversion. But the green line, which is weak inversion, it models the weak inversion very well. But as soon as we get into moderate inversion or strong inversion, the green and the red are nowhere near each other, so it's not accurate. And if we look at the strong inversion approximation, which is black, it matches the EKV model really well, right to moderate inversion, but then it's completely different, and this part isn't even real. It doesn't work below. You get imaginary numbers, if you will. So if you zoom in on it, you can see that weak inversion will overestimate your ID. Strong inversion will underestimate your drain current in weak inversion. That's okay. Equations are designed to get you close, and then you can change your biases and resistances from there to achieve your specification. So now let's talk about strong inversion, high power, high frequency, and this is what I would call your classic design. It's straight in the textbook. You should notice that the GM is exactly what you would see. And you can extract that pretty easily by taking the square root of ID and picking these 2 points and using the slope and solving for your threshold voltage. Now, unfortunately, VT in this case means threshold voltage and not thermal voltage. Now, how can we put all this together? Well, we can plot GM over ID. Here's your ID and here's your GM. In the lab manual, shows you how to do it. What's really easy to see though from this GM over ID plot is that where it's flat, it's weak. Where it's starting to curve down is the moderate, and the strong is over here. And if I kind of just take 2 lines from strong and intersect it with the weak, right at that point, what's that? 200, 300, about 400 microamps would be right at moderate inversion. And so if we wanted a low power, high gain design, low noise, we'd be over in weak inversion. If we wanted a trade-off, we'd be in moderate inversion. And if we needed something really fast, we'd be over here in strong inversion. So for any transistor, you can make this kind of plot and then very easily decide what drain currents are going to give you what inversion level you want. And the inversion level will tell you whether low noise, high frequency, all that good stuff. All right. So we can actually use that plot to show a maximum gain for a CS amplifier. So if we simplify the gain equation to the open loop, the gain in a common source amplifier is minus GMRD, right? Now how can I ignore the resistance of the op amp? Well, what I can do is make sure that the drain resistance is 1/10 the output resistance, and so it'll drop out. So if I do that and calculate that through, turns out the gain is GM over ID times VA, the early voltage, divided by 10. And so it looks like the same plot here, but actually now it's gain. So I just have a little bit over 100 gain. And that means for this transistor, no matter what I do, for this single stage transistor, the best gain I can ever get is about 100. And if I need to use 10 milliamps to make my device faster, the maximum gain I'm going to get is about 20. Moderate inversion, I can get about a gain of 71, or minus 71, minus 108. You can also choose any gain under this curve, but if you are given a gain, design a gain of 200 or minus 200. So you can't do it with a single stage, because you might think, oh, all I have to do is increase this RD. But what will happen is that RD will, which is in parallel with RO, will be limited by RO, because what you would do is make RD greater than RO, and then the parallel combination would actually have that RD drop out. So really, and what this does is it just saves you so much time, because now you know exactly what's possible and what's not possible. This procedure is in the lab manual as well. So let's just do a few design examples. I want to try to design a gain of minus 20 for all levels of inversion. And that means I need to pick the bias points, ID, VGS, resistor values, and the power supply. I'm going to assume Vin is a 10 millivolt sine wave. So in weak inversion, I can tell because it's flat. There's my my weak inversion equations. GM equals the drain current divided by NVT. And I just pull off 10 microamps. All right. And I could have chosen other things, but this is clearly in weak inversion. Well, I can assume the output resistance is infinite, and there's no gain, AC gain stabilization, so the gain is equal to this. And then I can solve for RD, and I can round that to 75 kilo ohms. Now, in order to design the power supply, we have to make sure that VDS is such that you're always in saturation. Well, how do you do that? Meaning this voltage has to be in relation to VGS, has to be such that you're in the constant current mode. So the way you do that in weak inversion is you make sure that VDS min is just 0.2 volts, just like a BJT. Where before, in order to be saturation in strong inversion, you had that equation. In this case, it just happens to be 0.2 volts. Now, of course, the gain is swinging around and changing VDS, so you have to add that. Then you have this voltage drop, and then you have that voltage drop. Now, yes, I did assume that there was no AC gain stabilization due to RS, but that's true at AC because I'm bypassing it with that capacitor. All right. I've also assumed RL is so big that it doesn't affect the equations. So if I solve for that, I can get a VDD of about 1.73, and I'm just going to round that up to 2 volts. Now I need to solve for that VGS. I chose VID, but in order to get that ID, I need the proper VGS. And so you just, using that equation, you solve using these numbers, which you can use. I've extracted them for you. I solve for a VGS of 1.455. Well, that's great. I have VGS, but VG is measured from the gate to ground. So I got to find VG. Well, it's VGS plus the voltage drop here, and I get 2.21 volts. Unfortunately, this is larger than my VDD. I have a few things that I can do, but what I'll just do is make VDD bigger, and I'll reduce RS to 20K. Since we're going for lower power, I'm trying to reduce the power supply, I'll reduce RS. So I'll recalculate it again, and I'll get VG of 1.66, and then make an assumption that R2 equals 100 kilo ohms, and solve for R1, which is 21 kilo ohms. So this is the complete design. I run it, and I get slightly different peak and trial voltages, and that's because GM is in fact not constant, because as VDS changes, your bias point is in fact changing. But it does match very closely. And this was the DC operating point, which matched hand calculations pretty well. You can download this file and modify it. You don't have to create it from yourself. And so you get basically a gain of -17 to -22, depending on which part. Now I could get the gains closer if I reduced VN, but that's inherently what happens when you short the series resistance here, or the source resistance, excuse me. So why is this gain changing? Well, the thing is that's because the bias point is changing. ID isn't really constant. So if I'm plotting ID and the gain depends on ID, right, then essentially your gain will change. Let's design one for a gain of -20, but in this case, let's do moderate inversion. So I'm just going to pull this off right from here. So I've got ID at 400 microamps. Now the thing is, I have equations for weak, I have approximations for strong, not really for moderate. So what you do is you use the weak, because in fact those equations are a little bit easier to deal with, knowing that GM and ID will be smaller than you're calculating. But you go through the same things on making sure that the power supply is large enough. Same thing happens to VDD. We can still reduce RS, calculate R1. So what's kind of great about this is the whole design is the same. I just have to change RD and R1, although the RD does look like it's from the previous example. In this case now you can see that I have in fact changed, solve for a new RD RS. In this example, I verified the point, we do it, and the gain is nowhere near -20. And that's because we used weak inversion, which overestimated GM, which made our RD value too low. Well, now, we know that RD is too low, so we can just bump it up. Because our power supply is bigger than we originally needed, VDS will still be allowed to be in saturation. And this gave us about a gain of -20, right on. And really, it only took me, I did these calculations, one simulation, did a simple calculation, another simulation, and then varied it one more time. So really, in 3 simulations, I was able to nail the gain. Now, this is strong inversion, and this is, again, classic above threshold equations. Everything that you see in the book for ID and GM relationships will work. Pick 10 milliamps. Now we using the same ideas, but I have RD now is 390. I'll run into 400 ohms. This is V threshold, not the temperature. And I have to solve for VGS using this equation rather than the weak inversion equation. Now, the thing is I have another thing changes. Instead of VDS min being 0.2 volts, it's really that RU in saturation equation, classic, that replaces that VDS min, right? VDS min is VGS minus VT, right, which is 0.4. All right. And sure, if you bump your supply voltage up a lot more than you need, you can guarantee that you'll be in saturation. But supply voltages are dropping in time. I mean, they're about 1 volt now. So this device, which has such a large VT, would be a little bit hard for a 1 volt power supply. So I get a VDD of 8.6 volts, and I round to 9. I have VG equal to 5.95, and I again solve for R1. Plug it all in. Now the thing is, now because this impedance is a lot lower, I have to increase the impedance of the capacitor so that it shorts properly at AC. If you kept this at 20 or 10 microhenries, it's not actually shorting like you would think. And so you get a gain of, that's about minus 20. And so there you have an example of strong, moderate, and weak inversion. Minus 20 worked for all regions because, let me come back, sorry. Because look at our original gain. Minus 20 gain is here, meaning it's valid all the way out to right that point, 10 milliohms. So anything in here, you can do minus 20. But if I wanted 100 gain, it would work up to here, but moderate and strong inversion cannot give me a gain of minus 100.